Hello everyone. Today we will simulate the Miller effect. Okay, and we will relate the theory and practical and see how to calculate dominant and non-dominant poles while there is a Miller capacitance. Okay, so this schematic I have created. Okay, so this one is DC source. This one is from analog library. This one also. This one also. The name of this instance is voltage control, voltage no voltage control current source. Okay, so go to the analog library and search this one. So you will get this one. So I have taken voltage control current source because MOSFET is by default uh, that only. Okay, so in first case I will simulate without Miller cap. Okay, so I will disconnect this one and I'll connect this one. Okay, so now in this case what will be the pole location? It will be simply 1 by 2 pi RC. Okay, so check and save. Okay, save. So let's calculate the theoretical value of this pole location. So I have calculated. So I have modeled that into pen and paper. Okay, so this one is 10 kilo ohm. AC magnitude is 1 volt and 1 picofarad. So what will be the pole location? It will be simply 2 pi RC. So it will come 2 pi into 10 kilo ohm into 1 picofarad. It's 15.9 megahertz. Okay. And what will be the gain? Gain will be nothing but minus GM into R out into B in, because this current will flow from this direction. So this will be plus and this will be minus. Okay. So it have a inverting gain. So what will be the gain? Minus 10 millisiemens into 1 kilo ohm into 1 volt AC magnitude. So it will come as minus 10. So in dB, what will be the gain? In dB, it will be 20 log gain of 10. So it will come 20 dB of gain. So theoretical value of this pole frequency is 15.9 megahertz. So let's simulate that schematic and check whether it's matching or not. Okay. So now go to the launch ADL. So go to the analysis and then choose AC analysis, shift variable frequency, shift from 1 Hz to 100 gigahertz. Okay. Now click OK and then run the simulation. I think it's simulated. Okay. Let me plot this on output voltage. Plot output. Okay. It's not simulated. Now it's completed. Okay. So you can plot from here also. Okay. So click the wire and simply plot voltage. So AC magnitude and uh, phase. Okay. So here you can see we had gain of 20 dB, 20 log 10. Okay, so it's 20 dB. Now what will be the pole frequency? So it's a 3 dB frequency. So 20 minus 3 will be 17 only. So let me mark this one 17 dB. Okay, so it's coming as 15.8498 megahertz. Okay, and what we had calculated? It calculated 15.9. Okay, so it's a matching only. So now here we are. Okay, now the in second part we are going to see the Miller effect. So I will disconnect this cap. Okay, and I will connect this one. Now check and save. So what is the theory behind the Miller effect? So this capacitor will be split into the input side and to the output side. So it will come input side and this one capacitor will come as output side. So let's see the theoretical aspects. Okay. So in second part, what I have done, I connected capacitance between a inverting gain. Okay. So gain of this one is minus 10 or 20 dB. So when you will split this one according to Miller theorem, it will come as Cc into 1 plus A. Okay. And at output side, it will come as Cc 1 minus 1 upon gain. Okay. So now what will be the net effective capacitance at input side? It will be 11 Cc, or you can approximate as A times Cc. Okay. So approximately we can see the pole frequency will get reduced by uh, with gain of 10. Okay, because capacitance increased by gain of 10, so frequency will be reduced by 1 by 10th. Okay, and what will be the output capacitance? It will be Cc 1 plus 1 by 10. It's 1.1 Cc, or approximately you can say only Cc. So I have calculated the theoretical frequencies. So first pole frequency is this one, 2 pi 10 kilo ohm 11 picofarad. Okay, so it will come 1.446 megahertz. And what will be the output frequency, pole frequency? It's a 2 pi into 1 kilo ohm of resistance, 1.1 times 1 picofarad. It will come 0.144 gigahertz. Okay, so this frequency are the theoretical frequency. So we will simulate and see, we'll see that whether these things are matching or not. So now let's simulate. So I have calculated this one. So according to Miller cap, input pole frequency should be reduced by 1/10. Okay, and this one will come at 0.144 times gigahertz. Okay, so again let's simulate. Okay, so it's completed now. Again, plot output voltage. So this one is output waveform. Now again the input pole frequency is dominant only. Okay, because in our calculation we have seen that this pole frequency is getting reduced. So this one is only dominant pole, and this one is non-dominant pole. So in Miller cap, input pole frequency is dominant and output pole frequency becomes non-dominant pole. So this one 3 dB frequency will be dominant pole frequency. Okay, so let's check value. So 20 minus 3 dB will be 17 dB. It's coming as 1.42991 megahertz. Okay, and what we had calculated 1.446. Okay, so it's approximately close to the theoretical value. Okay, so Miller Miller effect is like closely valid for dominant pole. Now let's check the second pole. So in magnitude plot, it's not clearly visible. So we will see in phase plot. So we know that at pole we get a 45-degree of phase shift. So this one is 180-degree. So first pole will give 45-degree. So here will be 135. So this one is first pole, and second pole will be at 45-degree. Okay. So there are two pole. One is going from 180 to 90, and then again 90 to 0. Okay. So second pole location is at 1.6178 gigahertz. Okay, 1.61 gigahertz. And what we have calculated? We have calculated 0.144. So a non-dominant pole frequency is not matching. So what is the wrong in our calculation? So the okay, let's see the what is wrong in our calculation. So While calculating capacitance output, let's calculate output impedance here. Okay, so we will apply a test voltage. We will ground the input voltage. Okay, so now let's say it's flowing a current IT, and there is one current here, and current are flowing through this direction. So let's apply KCL here. So VT by R2, this one, it's outgoing from that node, and what will be the this current VT minus V divided by 1 by SC. Okay, and what will be the this current? This will simply GM is voltage control current source. It will be minus GM into V. Okay, so and what will be the this node potential? So there will be one voltage dividing. Okay, so V will be across R1. So R1 divided by R1 plus 1 by SCC into VT. So approximately we can cancel this. Okay, so we can see that V is approximate equal to the test voltage. Okay, so please remember this one. So basically what we are canceling this one. So basically we are doing this capacitance short circuit. Okay, so we are doing this short circuited. So this whole voltage VT is coming to the this point V. Okay, now so what will be the approximate? This will become 0 because VT is V. So this will become whole term become 0. So only term will be left as VT by R2 equal to IT minus GMV. Okay. So after rearranging, we will get effective output resistance as G2 plus GM. So you see here what we were doing wrong. We were taken only G2, only R2, but we are getting one extra term GM also. So the new equivalent resistance will be 1 millisiemen of output resistance. Okay, so this one R2 is 1 kilo ohm. Okay, so it's 1 millisiemen, and GM value is 10 milli. Okay, so it will come as 1 by 11 kilo ohm. So output resistance is decreased. Earlier we had taken only output resistance as 1 kilo ohm, but that was wrong. So output resistance got reduced 1 by 1 kilo ohm. So now what will be the theoretical frequency? 2 pi R equivalent 1 by 11 kilo ohm into 1.1 picofarad. This is Miller effect. Okay. So now calculated frequency will be 1.59 gigahertz. Now let's check whether now we are matching with simulation or not. So it's a 1.59 gigahertz. Okay. So and here the second pole frequency is 1.6178 gigahertz. So it's approximately close to the 1.59 gigahertz. Okay. So now we can verify both the things. Okay. So directly Miller effect you can apply to the dominant pole. Okay. So dominant pole frequency will be you will get nearly equally and close. Okay, but during calculation of non-dominant pole, okay, output pole, you must short circuit this capacitance. Okay, and you have to calculate the effective output resistance at the output node. So you may recall that in two stage op amp when we calculate non-dominant pole, so we sort the CC and we see the effective output impedance at the output port. Okay, so now theory and simulation are completely matching. So while calculating dominant pole, you can account as 1 by 2 pi, and Miller cap will be A times CC. And while calculating non-dominant pole, you can take as CC only, and only thing will change at output resistance. Okay, so due to changing of output resistance, we are getting different. So I hope you understood what I'm trying to say. Okay, so anyhow, if you didn't understand or you see any wrong things, then let me know. Okay, so I'll try to make a better video. So thank you, and you can simulate also in your cadence and check verify. Okay, you can verify this one with voltage current voltage control voltage source. In that case scenario will be different. Okay, so in that case output pole will be different. Okay, so it's depends on whether we are taking voltage control current source or voltage control voltage source. Okay, so okay, bye, thank you.